is going to talk about Apple array allocation. So please go ahead.
Okay, so to start out, I'm going to talk about compiler as a library, a sort of new hopeful architecture for compilers, talk about the actual technical details for static memory management, no garbage collector, there's also no ownership the way Rust has, so hopefully easier on the programmer, and demonstrate some polyglot workflows. So a little bit showing off what we can do with Python alongside our array programming. There are three sort of inspirations. The first is that array languages suffer from a lack of embeddability. The idea here is rather than competing with NumPy directly, we turn to C. You may have read Kell's polemic on C. One of the things that C does well is you can embed it. People frequently call C libraries. You can compile C libraries to C procedures and so on. Also much easier for the programmer. You can use established libraries. For the array programmer, you can use established libraries. You don't end up being deprived for using this arcane language. It's a high-level language, but also informed by the backend, which I think is sort of not as familiar to Haskell side of things, right? So we ban certain things in order to get better performance, easier implementation, which, in Haskell world, if you say arrays of functions are banned, there's no type theoretic reason. I do think the sort of APL array side of things are sympathetic to this approach. And it's also a nice example of how you can do sort of whole pipeline compiler design, a nice trick for static memory management. And as it turns out, array languages are a good candidate for sort of new compiler architectures. In some ways, they're simple. You can do a lot of non-trivial stuff and beautiful stuff without relying on too much of other people's code. So rather than having a compiler which you call on a file to produce an object file, you could have a compiler which is a function which takes a string of source code and produces machine code. It'd be really nice if you could have another compiler call your compiler or just call out, right? So you'd be able to write procedures in the same source file because it's just a library function call. You'd be able to run code from your editor. You could send code across a network and it'd be a few hundred bytes, no RTS, no garbage collector that you need to deal with. Here's the, completely flat arrays. You only need one allocation here. So it just stores the rank, then it stores the dimensions, and then it stores the elements. There's no arrays of functions, there's no arrays of tuples of arrays, and there's no recursive data types. No lists are allowed in this language. So everything is completely flat, one allocation and one call to free. The language itself, just a demonstration, Kolbeck-Leibler divergence to show you can do non-trivial stuff. It's functional, expression-oriented, immutable. There's no recursion, and all looping is implicit, which will turn out to be important, but you can still do interesting things. Okay, so this is the compiler pipeline, very typical in many ways, straight from the compiler implementation in ML textbook. Basically, we generate the IR, which is a series of statements. We do liveness analysis to find out when arrays are live during the program, and then we insert free statements into it. That way we don't leak memory, and we don't need to worry about manual stuff like double free. This is the actual array. This is written in Haskell. This is pretty typical, I think. So there's expressions and there's statements. The statements used to read or write memory. It's close to assembly. There's jumps. And basically what we're going to try to do is try to treat arrays somewhat like registers. Compilers use liveness analysis on registers, which is not entirely possible. But if we do a little extra lifting on the compiler side, it ends up working out. So, so this is, right, this is the iterative liveness analysis, very typical. This is just for registers. You construct a control flow graph with your statements. Then with the annotated nodes, you can figure this out. The trick here is these aren't registers, these are arrays. However, because it's a high-level language, we can label them all. Within the compiler, we give a unique label to the array. And then from that, we'll be able to do, every statement we see which arrays it defines, which arrays it uses, and we can compute from there. This allows pointer aliasing, so we can access the data from one register and access the rank or the dimension from another. Because it's a unique label, because the label is internal to the compiler, we still get to treat it as the same, and we won't have any problems with, we won't have any problems tracking liveness. Oh, and there's no references. Because there's no references, no array can keep another array alive, so that keeps it straightforward. There is one big subtlety, which is that the frees must be reachable. So with registers, all you care about is where they're live. Here, we don't want to leak memory, which means we also have to worry about the control flow graph. So it's not enough to just say, well, it falls out of liveness here. We also have to make sure that the free statement is at a reachable part. It turns out if you make the loops jump backwards, this basically falls out, and this is more efficient on processors by convention. So if we try the sort of fraught, difficult way, we end up with the free being inserted where the live interval ends, but it's unreachable, which isn't good. If we make the loop go backwards, then the free is reachable. It occurs as soon as the array goes out of scope. So this actually turns out to work. The IR is generated by us. There's only a few cases. We have one function to write loops. There's only one way to write loops. There's also conditionals, which turn out to work. And we also have to avoid loops that do nothing. So empty folds are a type error, for instance. That's not a problem. We have to check for mapping over. But in this case, by careful management, we do get something which is memory safe, won't leak memory. Here's an example just to show that it does work. We can const one onto some generated array, and the compiler will, since it's immutable and copying, the array that's generated gets freed before the procedure returns. This is also fun. You can dump the intermediate representation inside the just-in-time compiler, inside a REPL, which I think is good for my debugging and also just a fun feature. And just to show off some of the advantages of this sort of compiler as a library embedded procedure, here's matplotlib. What I'm doing there is I have a program to generate numbers sampled from Gaussian distribution. As you can imagine, randomness is hard to debug. So we go to matplotlib, and with a histogram, we can sort of guess, okay, this is in fact normal a normal distribution, and this is correct code. You don't have to implement all of the existing established libraries in order to benefit from them. And you can write the code, which is more laconic, more fun, hopefully. This is, Bessel functions of the first kind. This is in a Jupyter notebook with R and ggplot. So the Apple code I don't think is the most elegant, but at the same time, you do see you can do non-trivial things within the language, even without explicit loops, even just with arrays of numbers. You can also read CSVs without, you read CSVs in Python, rely on something else. The idea here is, well, maybe array languages aren't the best for parsing, that's okay. As long as it's comfortable and fluent, we can still, or comfortable and fluent to do these sort of polyglot things, we can still have some of the advantage. This calculates inflation percentages. So we have one little, I think this is dyadic infix in J with a map, and all of the CSV processing, column selection is done in another language. Here is the 120 lines of R code for the just-in-time compiler. So it is, not perfect, but it's reasonably easy to add bindings to another language. The Python extension module is, I think, around 200 lines of C. So also not so bad. One of the things C does well, for instance, is the canonical implementation. If you write zlib, Rust has bindings to zlib, Haskell has bindings to zlib, and so everyone benefits even if you don't write C. Here, we'd like to have a canonical implementation. This is the shoelace theorem. You can compute the area of a polygon from its coordinates in Python and in R. So pretty much you write the same thing, you write it correctly, you write it once, and then you distribute to everyone to benefit, hopefully. You can also compile the same Apple code to an object file, call it from C. This is just to show there's no need for a runtime, there's no need to interface with a garbage collector. This is, it's pretty lightweight, it makes few demands of its host environment. Because it makes few demands of its host environment, the hope is it becomes more widely used. In terms of exporting and making array languages plausible for other environments, you want to export the ability to debug. You want to export things like, J has forks and trains, but you can't use them in a foreign language. The only thing you can export is, procedures, for instance. So that's a difficult question, but you do want to be able to export your debug facilities so you can print the, inspect the type. You can dump the assembly and within Python just to see, for instance, that loop fusion occurs. There's a no-SIMD, but basically this gets, you can debug things. Oh, thanks. Whoop. Okay, future work. I do think this is promising. I have not implemented this, but consolidating allocations, right? So if you have two ranges, you're concatenating them, and the second range is smaller than the first. So the output, you can allocate the output, you can allocate the first, and then when you're done reading from the first thing that you're concatenating, you could put the second argument into the space that the first one used. There's shape types. So since we know that iRange091 has size 10, iRange041 has size 5, in theory we could put the second argument into the slot that the first one has, which hopefully it would get on par with at least like reference counting in APL. I'm not sure anyone does this, but I do think there's performance boosts from static memory analysis. Okay. Questions? Oh, the future, yes. Okay. Oh. Oh, there we go. Oh no. Okay. Yeah. 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 Um. Yes. Or that's a different optimization. That's a better optimization. This is, I guess, a small example, but I think the idea is here. If you have arrays allocated over the course of the program, and you know their sizes, then you should be able to like fill in the blank spaces using some of this liveness analysis. Liveness analysis methods, yeah. Yeah, yeah. For the, yeah. Well, so you allocate the output. That has to happen. Then you allocate the left-hand side. Well, this is in this example. And then, you know, once you've gotten to concatenating the right-hand side, generating the right-hand side, you can reuse what you allocated for the left-hand side. I think maybe this example is too simple-minded, but basically the idea is, yes, there are programs where if you know the size via shape types and you know the liveness information, you could be able to do better allocations.
Yeah, let's assume you would. Oh, sorry. I think the better example for what I now understand what you want to show would be something like A plus B goes to C, where you have A and B and they all have the same shape or size, and then you could store the result in one of the arguments.
Yeah, yeah.
I think that would be, but that's what many languages would do.
Yeah.
Okay. Okay, thank you.
Yeah, so do you have an idea of where you would position the power, expressivity, and so forth of this allocation with things like region-based memory allocators and stack-based systems and ref counting versus garbage? Like, in the whole space, where do you feel like this falls?
So I think it's a little easier than Rust, I'd say. So compared to, I guess, like ownership, and then compared to garbage collection. I think the advantage compared to garbage collection is mainly you don't have to link in a big RTS. Compared to reference counting, I do think APL does good stuff there.
So if I understand correctly, I might be wrong. You are doing a sort of register allocation on arrays.
What notation? Or,
a sort of register allocation like technique for arrays, right? So how tuned is this procedure? Like, for example, you know, because I could have a big buffer, and then the next thing that I could reuse, it's a very small buffer, but this will occupy the big buffer. Are you chunking also the big buffer? Are you segmented it? Or you are just, even if the buffer that is necessarily for the reuse is very small, you are going to consume the whole buffer that is potentially very large? Or are you trying to figure out the best, the size that fits best, or how?
Well, I mean, if you have a slot, if you have like a slot of memory from an array that's like 1,000 elements, and then you have subsequently, you use part of that for something with 2 elements, if you know both of those sizes from the shape types ahead of time, you could just say, okay, and well now I have 98 over here, right? So I do think, yeah, that would be promising.
Okay, thank you.
So how fragile or composable and scalable do you think this technique is? Like, are you going to hit hard limits as you try to expand the language features, do you think, pretty quickly? Or is there a path towards either composing it with other types of technologies, or do you think you can continue to grow this to more sophisticated languages with less limitations?
I think some things can be worked around, like maybe it might be possible to do like closures, arrays of functions. I think with like, if you had arrays of lists, that wouldn't be possible. I think what I was trying to do here is you have an array, like a core array language, and then you offload the other stuff like linked lists to the host environment. So the hope is that this is not much of a limitation. You could add like algebraic data types. The main thing is no references of references, which I think that would be a hard limit probably.
Great. So the JIT compiler itself,
Yeah.
So that's written in C or?
So that's written in Haskell, yeah.
Okay.
Yeah.
So, okay. That was
Yeah.
This might be a very naive question. I don't really know what the ABI for like something like APL looks like, but why would I prefer this as opposed to just like writing some APL and like compiling it to something that I can then call into from OCaml or whatever?
Well, I do think you could probably have a similar compiler architecture for something like APL. I think the preferable part is, if you have a compiler as a library, there's a lot more you can do, right? So like if you have two languages in the same file and you can inspect the types in both languages in your IDE, that's much more convenient than what's typical now, which is like you have your Fuzark code, which you compile to Python. So if you've already, Whoop. Yeah.